So let's take a chance to now recap and revisit Dijkstra's algorithm and look at how we can apply the algorithm to this network here that we have on the left. So in this case, we have a number of different nodes, we have a number of different edges, and a number of different weights. And we want to identify the shortest path from S to T. So what can we say? So if we're starting at S, then the shortest distance from S to S is 0. So that we will have a value of 0 here at S. This will be our first permanent node, so we can draw a box around it. So what do we do then? So we've just made S with a value of 0 a permanent node. So our next step then is after a node is made permanent, we check all edges from it to all other non-permanent nodes. We update their working values if appropriate. So what nodes is S connected to? So it's directly connected to M, it's directly connected to R, and it's directly connected to V. So we'll now find out the working values at each of those nodes. And they're called temporary labels. So we have here at M, 0 plus 4 is 4. So we have a working value of 4 there. For R, 0 plus 7 is 7. And for V, 0 plus 3 is 3. So we now have working values at those 3 nodes. So we must figure out what do we do next. So this is our first step after the node is made permanent. After that then, next we compare all working values of remaining non-permanent nodes. So non-permanent ones are ones that have a working value. So we have a choice of 4, 7, and 3. So we identify whichever one is the smallest, and that'll be our next permanent node. So between 4, 7, and 3, 3 is the smallest, so that's our next permanent node. So we draw a box around it, and that's made permanent. That means it can't be revisited, and that is the shortest, that is the smallest, shortest value to get from S, wherever you started, to that particular node. So we're back again. So after this node has been made permanent, we check all the edges from it to all other non-permanent nodes. We update the working values if appropriate. So what's V connected to? So it's directly connected to T, and that's a weight of 9. And that's the only one that is directly connected because the others are directed edges in the opposite direction. So the only one that's going from V in the direction to another node is from V to T, which is 9. So we have 3 plus 9. So we're saying after a node is made permanent, we check all, update the working values. So that means we have 3 plus 9 is 12. So we'll have a working value at T of 12. Now, next we compare all, so once we've updated those, next we compare all working values of remaining non-permanent nodes to determine the next permanent node. So what working values of non-permanent nodes do we have available? So we have 4, 7, and 12. So the smallest of those is 4. So that's our next permanent label. So we'll make it permanent and draw a box around it. After a node is made permanent, we check all the edges from it to all other non-permanent nodes. So like what we did, so we have 4 plus 4 will give us a working value at n of 8. There we go. So next we compare all working values of remaining non-permanent nodes to determine the next permanent node. So what working values we have available at temporary nodes? So we have 8, 7, and 12. The smallest of these is 7. So 7 is our next permanent node. So here we go. So 7 is our next permanent node. So after the node is made permanent, we check all edges from it to all other non-permanent nodes, and we update the working values if appropriate. So 7 has a direct connection to n. So 7 plus 4 is 11. So now 11 obviously isn't an improvement on 8, so we wouldn't have to put it in there, but it's nice to keep track of it. 7 plus 8 is 15. So we can put it in if we want, but obviously it doesn't improve on 12, so it's no good to us. And then 7 then R is connected to V, but V is already made permanent, so that's of no interest to us anymore. So after that then, our next permanent node, so we look at all of our working values. So we had a choice of 8 and 12. 8 is the smallest, so that's our next permanent node. So we would draw a box around to make it permanent. So after node is made permanent, we check all the edges that it's connected to in terms of non-permanent nodes. So we have 8 plus 3 is 11. So we have a new updated working value at T, which is smaller than our previous lowest one. So we have 11. And next we compare all working values of remaining non-permanent nodes to determine the next permanent node. There we go. We have 11. All of our nodes are made permanent, and the shortest distance from S to T is 11. Thank you.